can hear me?
Yes, we can.
Yeah, okay. Thank you, Dr. I should say Professor Carino. It was my pleasure to be here, to be able to give a seminar here. And as you know, I love giving talks, particularly giving talks at Stanford. You know, I certainly enjoy my time many years ago here. Now, the only things I cannot see you, so I'm a little bit blind. I can only see a few people here. I can't really see you, so it's a missed interaction in person here. Now, it is, you know, when I think about ICME, it's actually a very exciting environment, and it just remind me my student days. You know, as Gianluca said, I was a student at Cornell, and I was doing my PhD thesis on for supercomputers. So I was from the computer science side of it, but we all part of the same supercomputer center, and where we actually had professors and students from various different fields, in applied math, from engineering, from operations research. So it was a very exciting environment. We actually get a chance to interact with people outside your own discipline. And quite often the big breakthroughs comes out of these interactions. So I certainly enjoyed the experience, and I hope you will enjoy the experience in the ICME also. So these are the happy student days. So really enjoy while you can here. Now, you know, one of the things actually I was interested in was combining for supercomputers, and what we were doing was really try to make computational math run fast, right? And it was and I got a chance to learn a lot about computational math, and you know, one of the professors on my committee, Charlie Van Loan, actually he wrote a book with Gene Golub from Stanford, and I understand he was the considered founder for ICME, right? So I grew up with that textbook, and you know, it was so interesting to learn about Cholesky factorization, you know, LU decomposition, SVD, and all the great things that Gene Golub and Charlie have done, right? So it was really enjoyable. You know, I hope you like. I understand that book is still being used, so it's amazing. So after so many years, it's like a Bible for major computation there, right? So now fast forward today, I'm doing AI, right? And when you think about AI, it's really computational math, actually. So AI really is a computation math problem. And so what I want to talk to you today is about how do we get high performance out of AI. And the AI we're talking about really is end-to-end AI here, okay? So what does that mean here? Let me just move to the next slide, if I can. Okay. So one thing, you know, it's looking pretty sure is AI is going to be everywhere, right? So when I was a student, AI was sort of in the cold winter at that time, and in the past, you know, about 7 to 10 years, it was another breakthrough, right? Because of deep learning, neural networks. Now AI is, you know, at that time, 7, 8 years ago, it was recognizing cats and dogs, right? And these were the breakthroughs, right? But today, you know, when we are in industry, I think you're interested in the talk because I'm coming from the industry. So not only do the research part, you know, looking at the research, the new technology, but also we interface with customers directly. We want to see how people are applying AI in the various different problems, you know, they have there. And effectively, that also means how they're going to apply the, you know, the computational math inside the broad industry here. So AI is going to be everywhere, and now it's not easy either, right? So there's many challenges, and you know, these are the opportunities for all of us, opportunities for me, for my team, and for all of you here, because it's good you're sitting on the you know, if you're doing computation math, it is a exciting area here. Now, a big part of AI and big part of computation math is you want to run things fast, right? So performance is actually very critical. Now deep learning specifically is a large amount of computation, and within the industry, there's a lot of people trying to develop different ways of accelerating AI. And the Intel is not, it's not different in this case either. So we actually invest quite a bit in AI. And so I'll share with you the hardware side first, right? So on the hardware side, when I think about AI acceleration, there are really three types of AI accelerations. One is you can add AI features to the general purpose hardware, which is in this case CPU. So we have the core on the client side, we have Xeon on the server side. These are all heavy duty general purpose CPUs. But in the past few years, we've been adding a lot of specific AI specific features. For example, integer 8 computation, bflow 16, vector operations. So there's a lot of things we're adding. And then in the next generation, which is coming out this year, is going to be a game-changing year actually for Intel, which is we're actually adding a matrix unit to the CPU side as well. So just imagine a CPU has another matrix unit embedded inside, which is very capable, right? And then to the other extreme, we're investing in special purpose accelerator for AI as well. For example, Habana, just give you one example. Habana is a company Intel acquired a few years ago. Their focus is designing a chip only for AI, only for deep learning actually, right? So you're going to run the deep learning operations very, very quickly. Now in the middle, because GPU is very popular as well for AI, right? For deep learning. So we are investing in GPU as well. So Intel has been doing integrated GPU for a laptop for many years, and now we're investing in discrete GPU for both the client side and the server side. And the Ponte Vecchio, our next generation GPU is called Ponte Vecchio. That has a lot of flops. The performance is really going to be a leadership performance, right? So we actually disclosed some performance demo a couple of months ago in what we call the architecture day, right? So we're investing a lot on the hardware side. Now, hardware without software is just a bunch of hardware. It's easy for me to say because I'm primarily a software person, right? Yeah, but I'm inside the hardware company here. Now, I picked up biking actually now it's almost 2 years now because of the pandemic. It's easier for me to go out and actually for me to go out during lunchtime, bike to Stanford. So you may see me coming to Stanford uninvited, right? So actually today I only have 1 hour break. I spend half hours biking through Stanford campus, right? So it's fun to do biking. Now when I started, I had a lousy old bike that was sort of very slow, right? So I upgrade to a much better bike, but that's not sufficient because if you want, because I cannot compete in Tour de France. If you want to go there, you need somebody who is good, right? Who is good at the biking, right? So the biker makes a huge difference in terms of speed. So in this AI case, a piece of hardware is not sufficient. You need advanced software to make the hardware shine and make it a combined software hardware to fly, right? And now what if you can improve performance by 10x? If you can improve performance on a bike by 10x, I think I can probably win Tour de France, right? If I can be 10x faster. Now, if you can be 100x faster, you will be flying at the flying speed, right? So there's a huge difference, particularly inside AI. The software together between software and hardware, you can make a huge performance difference. As I mentioned to you, I started my career on the supercomputer, but on the supercomputer side, we all also improve performance. But in terms of the degree, the amount of performance you get, the AI is really unprecedented. In my career, it's just amazing how much you get out of optimizing AI here. So here, this is what we do with Intel, right? So Intel, we looked at entire software stack, and our goal is to make sure our customers, they can run AI efficiently on our platforms. And as I mentioned at the very beginning of the talk, the problems customers are solving are really the end-to-end problems, right? And so what we want to do here is we want to cover the entire end-to-end pipeline. Now we do it for the entire software stack. So let me start with the middle of the stack first. I think you're more familiar probably with the middle of the stack, right? So for example, if you do deep learning, you all know TensorFlow, you all know PyTorch, right? So our job within our team is to make sure we optimize TensorFlow, PyTorch, and MaxNet, all of these very well on the platforms Intel is providing, right? And then because we cover a very broad AI and analytics, and we're actually doing more than just deep learning. Right? So the things in the middle, they are mostly deep learning and the traditional machine learning. For example, scikit-learn is for traditional machine learning. XGBoost is a classical machine learning, right? But we're doing more than that. We're also doing the enabling the analytics side of it, the NumPy, the SciPy, and pandas, all of it. So we want to cover the entire end-to-end pipeline so people can get the best performance when they solve their problems here. Now, in addition to enabling the entire software ecosystem, we also create our own software as well within Intel, right? So these are the things either we acquired recently or we actually created by our own teams. So for example, SIGOP is a startup we acquired about 2 years ago. Their goal is to do hyperparameter tuning to get the best performance out of different models. And the OpenVINO is a inference toolkit. And it was designed for deep learning inference only. So because it was only for deep learning inference, you can actually optimize much better, and it can actually support multiple architectures with that OpenVINO toolkit. And then the other one we've done is acceleration for low precision quantization. I'll talk a little bit more detail at the later part of this talk here. Now, the way to support the broad set of things is we develop all these different libraries underneath it. So the foundation of this is a One API, what we call One API, which is a new initiative coming out of Intel. It's an open initiative, right? Anybody can participate, and the specs are all open. Others can participate. Other companies can participate, can work on the specs together, and so it's open. It's an open system, open consortium, right? And then within that we have language support, for example, DPC++ as a language, and we also have a set of library APIs. So let me just take one example. Say OneDNN is an API for deep learning. So deep learning primitives like convolution and all these things are actually sitting under OneDNN. And with OneCCL, which is designed for communication for machine learning. So yeah, you can imagine when you do deep learning training, you have a large scale distributed computing. You want to be able to handle message passing in an effective way. And we designed a layer called OneCCL sitting on top of MPI, right? So the variety of One API layer, so the One API layer we have created. Now, we don't stop here. We want to go up because we want to meet the developers above us, right? So the developers will be maybe many of you, right, who are using these things, try to apply AI to solve a particular problem here. Now, how do we make it easy for all of you to do these things? So we create these toolkits. So we have a something called Big DL toolkit, and we actually can handle the pipeline in a more seamless way. And we also have the AI domain toolkits. For example, we have a Rexus, it's targeting the recommendation systems, right? We have another one targeting time series, and the PPML is privacy preserving machine learning, right? And we create all these multiple containers so people can just go from the container side, right? So that's give you the overview of the variety of software we're doing inside Intel here. Now, as I mentioned, it's about end-to-end AI, right? So when you think about end-to-end AI, I looked at roughly the 3 stages of the end-to-end AI, and then you start from data. If you're a data scientist, you start from data. All you want is some easier way of getting to deployment, right? You start from data, you do training, you do modeling, and then you optimize it, and you have a deployment, right? And so how do we handle these 3 different stages here? And we've been working on all 3 stages here. So let me just look at a few examples first. So we want to think from the user perspective. So what are the problems the user trying to solve here, right? So this is one example of a user problem. This is a case from Leica. You may have heard of Leica is a quite well-known studio, actually based in Portland, and they're doing animation. Right? They're doing animation, and they actually won Golden Globe Award and all that. It was they have quite a few famous movies coming out of this. And the problem they try to solve here is this. So they have the way they do animation is they actually build these objects first, and then they take a video of these objects, then they go from there, right? So because they build these objects, when you take a video, there are seams on these objects. So the way, as part of their workflow, they need to somehow manually clean up these seams, right? And so what we want to do is, so Kurt on the phone here, he is been working with them to help them figure out how to use AI to solve this problem, how to automate this problem here. And the automation is actually a pipeline here. So if you look at, you start from data, they have a lot of these images, they want to clean up the image in some way, right? So you do image data cleanup and augmentation, so you can use the data to support run your model here. And then you want to go through the step of data transformation. So the original data may not be the right data for you, so you need to do some original transformation to do this. And then you get down to a model training piece of it. Now, I want to go through this in a little bit more detail, so we can sort of get grounded, to get a understanding of what the actual problem we're trying to solve here. And in this particular case, a real user like they don't need to go from a model from scratch, right? So they actually take a pre-trained model. In this particular case, there's a model called EfficientNet. And then they do transfer learning, because EfficientNet has been trained using other data set already. And then they use their own data to fine-tune the model through transfer learning. So the amount of data is actually not that huge, right? And they have some way of, so this is going through transfer learning, and then they go through the tool we have, Intel neural compressor, then go deployment from there. So this is one flow of doing this. Now, another example, I want to go through a few examples more quickly. So another example we have is a Twitter Rexis Challenger program, and this is all open challenge, and the data is provided from the pipelines from Twitter, right? So in this case, I just want to call the difference. It's also pipeline. They have a lot of data, billions of records, and go through, again, data processing phase, feature engineering, and so on. Now, the training part, the model is actually different. The model is LGBM. It's a model created by Microsoft, and it's actually using the classical machine learning. It's not a neural network, right? So classical machine learning today is still widely used so when we think about AI is really more than deep learning. AI is deep learning as well as classical machine learning. Now, let me look at another example. So this is another example where our team work with MasterCard. And the MasterCard, as you know, as you can imagine, is a lot of data, right? They have like more than 100 billions of records of, I guess if you have a MasterCard, your data is being included here, right? And then you probably don't know what kind of things people are doing with the data. Maybe someday you get a flyer saying, hey, do you want to buy this thing? So maybe we are guilty because we enable them to do target advertisement at you here, right? But the amount of data is huge, and then they want to create multiple models here. So in this particular case, is a set of models. NCF, you may have heard of it, is one of the very well-known recommendation system, right? Recommendation model here, and the autoencoder and all these. So they have so they use TensorFlow, and now the difference here is they already have big data. So in the real world, people started big data more than 10 years ago, right? More than 10 years ago, they start with a lot of data, and then they already have an infrastructure running all that big data. And now the question is, can we do deep learning on top of the big data in the big data environment as well? So we created a tool called BigDL, which allows the customer to construct their deep learning pipeline in a very seamless way, going from data processing part all the way to model and deployment. Okay, so I'll give you these three examples, a variety of type. You can imagine many different type pipelines here. Now, how do we optimize for each of these stages here, right? So first, as I mentioned, at the high level there's a data stage, right? So how do you handle data? Now, as we have seen, the amount of data is growing very significantly, right? Because you must have seen a lot of places where people show you all these charts. Data is growing exponentially, and the majority of data has not been effectively utilized. Now, in other hand, if you go from data to the kind of compute we have today, quite often the data scientists are involved in this, right? In different ways. So one way of doing this is quite often when you do kind of a data feature engineering, the data scientist actually is interacting with the system to do this. So you want to make these things fast. So you don't want, because the data scientist resources are very valuable. It's more valuable than the machines, right? And you may have learned the hard way from your perspective. When you create these things, your time is more valuable than machine time, right? And so what we want to do here is we want to make your interaction fast, right? So how do we do these things here? So one key component of this is when you do feature engineering, a lot of these things are handled by, for example, by pandas. So there's a lot of SQL, operations going on here. And so how do we? I'm sure you know about pandas. How do we run pandas faster on your machines, right? So we have a new open source project called Modem. And the Modem is designed to do two things. One is to design in such a way that it's compatible with pandas. So it's the same API. You can, whatever you run on pandas, you can use Modem for that as well. And so below that, we improve performance. So we improve performance even on a single node. So we actually shipped something called Data Science Workstation a few months ago. So within that, you can actually start your analysis on a single workstation, right? On a single workstation, could be a laptop, could be a desktop, and you do analysis from there, and you can run things very efficiently. And particularly for some of these desktop workstations, and the amount of memory is very big, and particular persistent memory, they can get to 6 terabyte of memory, and the amount of data you can process is very large, actually, right? So you can start from there, and the optimizations we have done within Modem allow you to process large amount of data even on your single node. So that's one aspect of Modem. And the other aspect of Modem is we want you to be able to scale out in a very efficient way. So how do you scale out from your desktop to the cloud, for example, to AWS, right? Where you can get more node resources from there. So what we want is to make it easy for you to go scale out, right? So in this particular case, all you need to do is having a one-line change, and you can scale out to in the AWS environment, right? So that's these are the kind of thing we're doing, which is how do you optimize and getting large amount of performance, and how do you make it in such a way that the users will find it easy to use this stuff, instead of you don't need to write assembly code for this, right? And the way we do this here is, if you think about Modem specifically, is we're going through it's underneath it. Underneath it is all about data frames. It's all about data frame algebra. The different operations you do on the data frame, on the data frame side. For example, you do sort operation, you do join operation. How do you make these operations run more quickly? And then once we have the core of these optimizations, then you can support multiple APIs on top of this. Some of these are pandas API, some of these can be other standard SQL API, and so on. And then below that, you can sit on top of variety of infrastructures available in the industry. Now, let me look at the second part. So the second part is about modeling, and modeling usually has the training component, has the inference component to this as well. Now, if you think about, that's where a lot of the computational math comes in here, right? What is the most basic computational math you want to do well here? Right? It's actually matrix multiplication, right? Matrix multiplication. How do you run matrix multiplication fast on the large compute system here, which is not that not that straightforward, right? Because if I think about mathematically, all you need to do, all you have is C equals A times B. But in reality, how do you map that operation on the compute system, which is very complex, right? We're talking about, and nowadays for deep learning, the amount of compute we have underneath is huge, right? And I worked on supercomputer before, but supercomputer compared to the machine learning engines we have is nothing, right? I mean, these are the huge amount of compute flops we have available for these accelerators. These are deep learning accelerators here, right? And so if you think about, so how do you run matrix multiply fast is really a core to getting deep learning performance pretty much anywhere, right? And the way I'm just giving you one example here, which is what we've been doing on the GPU side. And on GPU side, so there are actually two ways of looking at this thing here. One is there's a computation part of it, which is usually easier to understand, right? So you have a matrix here times another matrix. How do you break up the computation in such a way that you can map the computation to the underlying machine in a more parallel fashion? Because in the machine below you, there are many of these execution units, many of these matrix engines, right? There are tons of these matrix engines. So it's really a supercomputer below there, right? So how do you break things up so that you can run these in parallel? That's how you speed things up, right? Now there's a little bit complexity here, because when you break these things up, the machine is a little bit hierarchical, right? You have a single GPU, which consists of multiple XE, what we call XE cores, and then each XE core we have multiple of these blocks and multiple of these matrix engines. So you need to decompose in such a way that will map these things well. Now that's only half of the problem, actually. So actually that's the easier part of the problem, which is how do you decompose computation into the machine below that. The harder part of the problem is actually the memory hierarchy. So thinking about data, right? Large amount of data. Managing data is key to getting the best performance. And on these machines, the data, they have a hierarchy. The closest, fastest, but it's also smallest is these registers, right? And then in the middle, these are a little bit bigger, either L1 cache or local memory, a little bit bigger. But also, a little bit bigger, a little bit slower than registers, right? Then you go up, you have more memory, let's say global memory or L3 cache. These are bigger memory, but slower, or slower than the cache and so on, right? So how do you decompose a tensor in such a way that you actually operate your data as much as possible from your faster layer of the memory hierarchy? So that's another key. So how do you do both of these things right? We spend quite a bit of energy, and we have experts who've been doing this stuff for many years to fine tune these things, right? So we have our library called 1DNN, which is actually derived from another library called 1MKL, and the Intel MKL library has been around for at least more than 20 years, and it's been heavily optimized, right? So I actually remember one day I was attending a retreat from Stanford CS department organized a retreat on AI. So I went for that retreat, and there was a student talking about building a new exciting kernels and all these things. And he said, "Oh, I was trying to build something to beat MKL, but eventually he could not beat MKL." And he said, "Oh, because I could not beat MKL, I just started using it." Right. So it's not easy, because we spend a lot of engineering resources to fine tune these things to make it fast. It's not non-trivial, right? Now, having these kernels is not sufficient. Okay, so we also, when you think about a deep learning model, the deep learning model is actually a workflow, right? A workflow, it turned out to be a graph here. So you actually have a graph, and then the graph has multiple operations here, right? So you have start from sum. To give example here, sum, ReLU, and you have conv, one by one, this convolution operation one by one, your batch norm, rate rule, and all these things here, right? So as I mentioned earlier, the two things here. One is computation, the other is memory hierarchy, right? And the way the original program was written, it's good for computation, but it's not really good for memory hierarchy, because if you do, let's say if you do conv one by one followed by batch norm, right? So you traverse all the data in conv one by one, and then you're done with it, and then you traverse data again in batch norm. That's not the right thing to do. So ideally, you want to merge these things. You want to look at a small amount of data. You do two things together, right? This is what we call fusion. That you're fusing these operators, so you can effectively using the memory hierarchy here, right? So we do a lot of fusion. So there's something called batch norm folding. Basically, you fold operation into another operation, and then you do conv. I won't go into details because effectively you do a lot of fusion, blocking fusion, so make the memory hierarchy work more effectively. So this is what we do on the CPU side. We do on the GPU side as well. So this is very generic way of looking at it. Really, there's no difference between CPU and GPU when you look at the fusion side of it. Now, the parameters may change, but the idea does not change. And one of our goals here is to get to the best performance, right? Because we the overall system has hardware and software, right? Hardware has certain capabilities. Let's say hardware has certain number of operations you can do in parallel in one cycle, for example, right? Has certain amount of memory here, right? And so it has a certain capabilities. What we want to do is get the best performance out of that piece of hardware. So this is what we call roofline. So the roofline is a analytical way of looking at the entire system to say, what is the best potential performance you can get out of a machine here? Sorry, my iWatch came up. So our goal is by going through multiple of these operations, these optimizations, you get to the roofline here. Now, let me just go with one example just to show you here. This is one of these recently, sort of analytics side, right? So this is a graph analytics, and as you may imagine, a lot of data is actually naturally mapped to graph, right? If you, let's say you have a social networking, you're friends with this person, now you are one node, that person is one node. Once you're friends, you're connected, you have an edge in between, right? So many problems can map to, a lot of pharmaceutical, drug discovery problems can be mapped to graph also. So graph analytics is pretty important. And in this particular case, what we're trying to show here is, let's say the baseline is running, the second row here. Second, it says 1.0. The baseline is running on the 32 node parallel cluster already, right? And then now, this is joint work actually with the Katana Graph, another startup doing Intel joint collaboration with the Katana Graph. So what they have done is you can shrink your cluster into a single node. So on the single node, the difference is instead of adding more nodes here, we're adding more memory. So we have something called persistent memory, or Optane persistent memory. So once you add more memory into the node, you're actually able to do a lot of work on a single node. And in this particular case, a single node with larger amount of memory is almost, it's actually 1.8x faster than a original cluster with 32 nodes, right? So this shows the power of moving data. Moving data effectively can improve performance a lot, right? And then you can also scale out by adding more nodes to it. For example, you go from 32 nodes, you can get to, from 32 to 64 nodes, you can do 1.4x, right? So in this case, adding double the number of nodes is not as good as, actually adding more memory here. But if you go further, go to 128 nodes, you can, scale out even further, right? So the two ways of doing this. One is scale up on the single node side, the other scale out. So these are the sort of base technologies we can use to improve performance here. Now, having done all of these things, right, optimizations inside library, the graph optimizations and all these. Now, one important thing for us is to reach the software everybody is using, right? So as I mentioned to you, we actually optimize a lot of the most popular software in the industry, right? PyTorch, TensorFlow, and all that. So this just give you example of integration of optimizations into something like PyTorch. I know a lot of people in academia actually are using PyTorch, right? And so we actually have a two-pronged approach here. One is we upstream all the changes into PyTorch, right? So if we have a new operation, we put in the one DNN, and one DNN is already becoming a default inside PyTorch. You can just use it from there, right? And if we add a graph optimization, we add the optimization into a PyTorch. You go from there, right? And then we also have another thing called Intel extension for PyTorch. So think about this way. Think about this: a stock PyTorch has as many things as we have upstream. And then we also have another Intel version called Intel extension for PyTorch, which has the advanced optimizations we have come up with. And some of these optimizations will potentially eventually be upstream into PyTorch, and some of these optimizations may stay there, right? And for different reasons, right? So for example, our CPU optimizations are all going to be upstream, but our GPU optimizations are going to be inside the IPEX because the PyTorch team, they want to structure the different accelerators in different ways, right? So this is sort of a two-pronged approach for us to optimize something like a PyTorch. Now, let me go to the deployment side, right? So once you have a model which is very well optimized, so how do you deploy the model on your platform here? So for example, if you want to let's say continue to use either PyTorch or TensorFlow for deployment, right? Because for deployment you still have a lot of choice. So quite often, if you build a model inside PyTorch, you may want to still use PyTorch as your inference deployment as well, right? So in that case, we also have create another tool called Intel Neural Compressor, and that's very much supporting these major frameworks like PyTorch and TensorFlow. And the goal of the neural compressor is to make the model even better, right? So we want to make the model better in different ways. So one way of doing this is, let's say, you start training with something like floating point 32-bit, right? So you train inside floating point 32-bit, but when you come down to inference, you don't really need to have floating point 32-bit, right? All you need is integer 8, right? And you can imagine going from 32-bit to integer 8. Even the data size is a factor of 4, and you may get roughly 3x performance gain, for example, right? By doing these things. Now there's it's non-trivial actually to go from 32-bit to 8-bit because the information content, which was originally stored in the 32-bit, now you have to squeeze that into a 8-bit thing, right? So how do you calibrate that so that you still get the same accuracy? You don't want to change the model accuracy, right? So you want to preserve the accuracy as much as possible, and while still having the smaller thing here, which is a 8-bit. So that's what we call quantization, which is so today, for the most part, we're able to get to these models within 1% loss of accuracy. Right, you can. So quite often people say, "Hey, it's as long as within 1%, they're happy," right? But the process may not be straightforward. So the next slide, I'll show you how the tool works here. So this is one way of doing this is quantization, and the other way of doing this is pruning. So you export sparsity. Many of these models, these are very sparse. So within these models, these are all matrices. So back to matrix computation, and you probably learn a lot about not only dense matrices but also sparse matrices, right? So how do you create more sparsity? Because you can do faster computation because if the matrices are sparse here. And then there's another way of doing this. You can do distillation. That means you have a bigger model. Can you have a smaller model which does the same thing here? So the variety of things you can do here. And the way we do this is instead of the traditional way of doing a lot of manual, code change, sometimes you have hundreds of lines of code you have to change here. We actually have a GUI, which we actually inside the GUI, we actually do a lot of things automatically for you. And so there's auto quantization going on, and then it will make it easy. So we actually had a demo in the event that Intel had recently, a couple of months ago, called Intel On, and they showed you can actually get more than 10x productivity gain by doing something like ink here. Okay, now sometimes sometimes you want to do something different when you do deployment. So we actually have another tool, as I mentioned earlier, called OpenVINO, right? If you can also use OpenVINO for inference, for inference and deployment. As I mentioned earlier, the OpenVINO can, for certain models, can have a better performance, particularly smaller models, because OpenVINO can be designed in such a way, because it's inference only, so the overhead can be smaller than the framework side, right? So you can do the overhead of framework will be more pronounced when you have a smaller model. So therefore, the smaller models, OpenVINO can have a meaningful better performance over there, and also it supports multiple targets, right? So if you have a different hardware you're looking at, if you want to do inference on the CPU or inference on the GPU or inference on the VPU, you can use the same API to do all of these things here, right? And then on top of this, you can also do for the same inference job, you can do this on multiple of these hardware targets at the same time as well. So these are quite advanced activities, the we call multi-device manager to allow you to do all of these things here. Now,
Wait, sorry to interrupt.
Yes.
I wanted to mention the 45 minutes mark.
Yes, I know. I'm just running. I want to run through this, and there's a few, probably three slides left, and I'll get to the question part. Okay, so going forward, it's just tremendous amount of opportunities we have here, right? And this is something, if you follow LinkedIn, I posted something recently, actually last week, on this blog. Intel is working with another company to look at the astronaut health, right? If you want to explore Mars, and what will be the impact of cosmic radiation on people, right? Not only astronaut, maybe someday all of you guys will have chance to go to Mars, right? So you want to know, are you going to get the radiation, what's the impact or not, right? So in this particular case, they're using federated learning to work on this problem here. And the other thing I found interesting is I reshared his post last week also. Niels Reimers is a researcher from Hugging Face. Hugging Face is a company which is specialized in natural language processing. They maintain a lot of models. They are one of the biggest players in natural language processing. So he did some research on what OpenAI presented recently on these different models, and what he found, I find it very fascinating, because it related to sort of the dream I have, which is AI everywhere, right? What he found was, if you use some of these models, it may cost you $1 million to do the work, right? Like a third, the fourth line, the Da Vinci line, and now if you happen to find a cheaper model, and the cheaper model, which actually does gets similar result. I mean, the performance is 52.7 versus 52.8. It's sort of very much comparable, but you only need to spend $3 on this, right? So this gives me a lot of hope. Just says there's a lot of places for creativity, right? If you figure out the right thing to do, the kind of change is really huge, right? And if anybody can spend $3 to do deep learning, and that will really help AI to be everywhere, and you don't have to be super rich company to be able to do this, and anybody can actually run AI here, right? Now, talking about super rich, Stanford, right? So that's that's another project we're working with. I don't know whether Allison's here or not, and we started working with Allison and her team, and this is another fascinating example, because you can use machine learning cardiovascular research here, right? This is the targeting cardiac surgery, right? So and it has a bunch of Luke. This is what Luca sent us. If you have more questions, talk to Luca. You probably know him in ICME, right? And so the current way of doing things is using a simulation approach. It costs a lot in terms of time, right? Takes days or weeks to get back. Can we use AI to shorten the process, to shorten this? And this is something Kerr on the phone is working with Luca and others, and so this is a very exciting opportunities we can have here. So to wrap things up, it's as I said, we are at the right time, right? It's the right time, right place. AI is going to be everywhere, and there's a lot of different kind of innovation going on here. And the last thing, but not least, really, it's really all about computational math. And we are doing computation. AI itself is a computational math problem, and we are also using computational math to help solving the computational math. So there's a second level derivatives here, right? So with that, and if you want more information, you can find it on ai.intel.com. And on the bottom right, I just want to do a plug here. We're also hiring, and we want to hire the best people we can find. And obviously, we want to have Stanford people. So if you are interested, go to their website and or let us know. We'll be very happy to talk to you. So with that, I have 10 minutes left. Questions?
Thank you very much, Wei. So there are a couple of questions in the chat. I don't know if you can see it.
Yeah, I can see some of them here. Let me see. Okay, so what is the typical approach to start optimizing a large platform? For example, PyTorch. Is there a team dedicated, a single person gets started, or a application driver? Okay, so it's not. Okay, so let me answer the question the way I understood. So there may be two levels of interpreting that question here. One level of interpreting question is optimizing PyTorch itself, right? And so I do have a team. So we have a dedicated team optimizing for PyTorch, and it's the amount of work is non-trivial. Actually, there's a lot of work involved, and not only optimizing it but also advancing the capabilities, right, of for PyTorch, and usually there's a application driver for this, right? So we actually work with many customers, as you can imagine. We work with the major CSPs, we work with a lot of enterprise customers, and so they will come us to say, hey, I have this particular application, I want to get a better performance. What can you do about it? So we end up analyzing the application. We find out what's going on with the model, and what are the bottlenecks, and what are the. So that's how we create the new optimizations for these things here. So yeah, so that's the. Yeah, I hope I answer your question here.
Yeah, no, this is good. Yep.
Okay.
I was curious about what somebody that works in your team would do, basically, their days, right? How do their days look like if they work in your team?
Yeah, it will be very fun, actually. It's I think one thing, it would be okay. So there are different opportunities within our team, right? So one key thing is getting these things run fast, right? So you can optimize a particular kernel, right? For example, convolution kernel. If you're really into computation math, right? So convolution kernel, for example, can you get the best out of the convolution kernel performance on CPU or GPU, and you create a lot of different optimizations for doing this. And if you're more of a bigger optimization person, right? So if you look at the graph level optimizations, and you can have a different algorithms for optimizing these things also, right? And then we also move up You know, like what Kerr is doing is we have data scientists, right? People who actually work at the algorithm level. So can you define the algorithm in a different way, and maybe that will drive different ways of getting best performance on our platform also, right? And then we also invent new tools, right? Invent new tools for doing these things. You know, this is not only library, not only frameworks, but also tools on top of the framework. Let's say, can we create a toolkit for graph analytics that would give you best performance, or give you best not only performance but also productivity. You know, make it so easy. People can just, you know, can you get to a low code or no code environment, right? And when you solve a problem, all you need to do is do a GUI, plug a few things, and all of a sudden they have a model, you know, optimized for this, right? So there's a multiple levels of things one can do in the field of AI. And within Intel, we also try to apply AI in different, you know, problems we're trying to solve here. So I just share one of the things, you know, example here. Let's say, you know, we have a compiler team which is trying to do. Actually, we have a compiler team within the deep learning side also, right? Deep learning eventually becomes a compiler problem, because you want to take a graph. How do you generate coding quickly, right? And can you apply AI to solve these problems? Right? Can you apply AI to, can you create AI to generate code automatically, right? And so there's a variety of opportunities over here.
I want to go back to one of the questions in the chat that Asavari asked earlier,
okay.
Which is, and I guess you already answered, but what is the customer base for the data platform that you're building? And especially for not tech customer base, how would Intel handle things like explainabilities, for example?
Yeah. So that's a great question, right? So the way we view this is the AI customers initially, they were all the, you know, the PhD, machine learning PhDs, right? They're the people who got very well educated in data science. They may have a statistic PhD or whatever. They, you know, and they'll create new things and all that, right? So that's the beginning of deep learning, right? That's one set of customers, and quite often they are in the major, you know, cloud service providers, in research labs and all that, right? But the AI market is huge, right? And we're talking about AI everywhere. We're talking about scale out, right? Scale out. And so we want to be, the people we interact with even today is beyond these PhDs already. The people interact with, you know, for example, a data, people who happen to have data in some organization, in some company somewhere, right? And they just read about, you know, AI a little bit here or there. They may have taken Andrew Yin's class, you know, they know a little bit about machine learning, right? But they're not really deep machine learning researchers and all that. So can we? So these are the people we're targeting. Actually, we're trying to expand our coverage to go from there. So we want to go from all the way from anyone, you know, to who can actually that makes the whole thing exciting, right? So make it, it's sort of the invention is driven by the need, right? So we have the need here. We have the need here. So if somebody can figure out a way to automate the process where you can get the AI benefit without, you know, making people do a lot of work, that's going to be the ultimate thing we're looking for here. So our customer base is really expanding. It used to be a few years ago, we're still counting. I say, hey, oh, well, we're lucky we got this customer who's doing this thing here, right? So today, we can't even count the customers. It's like sometimes, you know, because people always ask us, say, who's using our stuff, right? And they want us to measure, you know, everyone has to justify our value, right? Who's using our stuff? And we say, oh, these are people using stuff. And quite often we don't even know. The only way we know that is somebody happened to send an email to somebody in our team, say, hey, I happen to use your stuff. Here's what we're doing here. So it's a good sign, because it's out of control in that sense. We don't even know who's using our stuff anymore.
Unfortunately, I imagine that most of the people that contact you are for complaining about something that doesn't work. So
yeah. The happy customers are rarely go talk to you, right? Usually the people who complain. The successful one, they don't tell you. Yeah. They're just happy. They're quiet, you know.
That's right. Okay, well, I guess we'll stop here. It's the 5 p.m. mark, so I wanna thank you again, Wei, for sharing this with us. Again, if anybody's interested in connecting, you have the QR still on the side or on the slide, or you can get back to me, or Stacy will be happy to forward your questions to the team at Intel.
And you can find me on LinkedIn. Nowadays, it's so easy to find people. So you can, I'll accept everyone from Stanford, particularly people who attend this seminar.
Sounds good. Well, thank you again, and thank you all, and I'll see you all next week.
Okay, thank you.
Bye-bye. Have a good evening.
Okay, bye.